Okay, this is a review of Chapter 4. I'm going to make a bridge map to help you kind of organize what the chapter is about in your mind. As you are making your map, keep in mind what questions you might have about this. So this chapter was about solving systems of equations and inequalities. So I'm just going to call it systems because they're linear, but some of them are inequalities and some of them are equalities. I think that there were basically two ideas, maybe this chapter. So I think the first idea I would say is solving a system of linear equations. Why did it do that? And then the second big topic is inequalities. And inequalities, when you solved those, you had either just a single inequality or you had a system of inequalities. All right, there are, as you know, three big methods for solving systems of linear equations. The first big method is solve by graphing. And the second big method is solve by substitution. And the third big method is elimination, or sometimes your book calls it linear combinations. Linear combination to your book just means that you have to multiply before you add. Okay. Within those, there's also the idea of no solution or infinite solutions. So the kind of, I guess it's if they have the same slope. And then also within that, for all of those, there were also word problems or real-world kind of problems. Okay. When you are graphing to solve a system of equations, you are going to be looking for the point of intersection. If they do not intersect because they're parallel, then that means there is no solution. If, as you're graphing, you find out that they are not only not parallel, they have the same slope, but they also have the same y-intercept, then that means they are the same line exactly, and they have infinitely many solutions. When you are graphing to solve a system of linear equations, you want to remember to manipulate your equations so they look like y equals mx plus b. So the first thing you should do is called solve for y. And what solve for y means is you want to get y by itself. I'm going to pause here and do an example of what that means. So let's say that you have 2x minus 3y equals 12. If I want to get y by itself so that I can graph this, I would set up my railroad tracks, and I want the y by itself, so I first want to get rid of the x's, so I would subtract 2 x's so that they can go over to the other side of the tracks. Right now they're added because it's a positive 2x, but I can subtract them to move them to the other side of the tracks. So I do that and I get negative 3y, because the x's subtract away, equals, and I like to write the x part first so that it looks like more like mx plus b. And then I see that I have a negative 3 in front of my y. A lot of people try to add 3, but this actually means negative 3 times y, so I want to do the opposite of times. So I'm going to divide both sides by negative 3, and I get y equals 2/3 x minus 4. All right. The next method, so you graph the 2 lines, you solve for y, you graph the 2 lines, you find out where they intersect. The next method is substitution. For substitution, you solve for the loneliest variable. And then you substitute into the other equation. And you solve for the other variable. So I'll do an example of that. If you have 2x plus 4y equals 10, and you have x plus 2y equals 5. No, I'm going to change this. Sorry, that was, well, it's not bad, but I'm still going to change it. Let's say you have x plus 3y. Oops. Equals 7. So then I see that the loneliest variable here is x. So I have x equals, I'm going to subtract 3y, so the x can be by itself. 7 minus 3y. I can't subtract those because they're not like terms. And then I take that and put it into the other equation. So I have 2 times x plus 4y equals 10. And instead of x, I'm going to write 7 minus 3y because that's what x is equal to. Then I'm going to set up my railroad tracks. I'll distribute. And I see some like terms, so I'll add some like terms. I'll subtract 14, so I have negative 2y equals negative 4, because 10 minus 14 is negative 4. And then I'll divide by negative 2, and I get y is equal to 2. And then in order to figure out what x is, I can put y equals 2 into this definition for x that I have. So I have x equals 7 minus 3 times 2 is 6, so x equals 1. And so then my ordered pair would be 1, 2. All right. The elimination linear combination method is you add your 2 equations together. One of your variables will drop out, and when you and then you solve for the other variable. This only works if you have the same but opposite coefficient in front of one of your variables. So that when you add the two equations together, that variable drops out. I'm going to do an example of that kind of equation. So let's say we have 2x plus 4y equals 10. And I'm actually going to do the one that I had written originally. So that one was x plus 2y equals 5. If I multiply this equation by, let's say, -2, if I do that, I'm going to get a positive 2 coefficient in front of this x, and I would have a -2 coefficient in front of the other x. So that's good. And then my other equation, I just copy it down as is. And then when I add everything together, my x's drop out, so I have 0x. Oh, and look at this, my y's are also dropping out, so I have 0y equals 0. So I wound up with a very true statement. 0 is definitely equal to 0, but I don't have any x's or y's. What that means is that these are actually the same line. So this is infinite solutions. So the thing to keep in mind over here when you have infinite or no solutions is that you have a true equation with no variables, like 0 equals 0. That means that you have the exact same line. For a parallel situation, you have no variables, but you have a false equation, like you might have -3 equals 0. If you get to that point, then you have no solution. If you get to the point where you get a true statement but no variables, then you have an infinitely many solutions. All right. Then the other type of thing that you had here was word problems. And for those word problems, I really recommend that you make that model. So this box, this middle box, is what question you're trying to answer. In this box, you list your variables. In this box, you think of equation 1. Somehow in the words, there's going to be like something that is equal to 50 or something, and then you can set up an equation for that. And in this box, you would have equation 2, and then in this box, you solve it. It's just a really nice way to organize your work and keep straight what you're trying to find out. All right. Inequalities are just, they look like equations, but they would have a sign like that instead of an equal sign. So let's say you have y is less than 1/2 x minus 4. If I were going to graph that inequality, the first thing is that I would have a dotted line. And the reason I would have a dotted line is because the borderline should not be included, because I just want things that are less than that line. And then I would do just like a line. I would start at the y-intercept of -4. I would have a slope of up 1/2. And then I would make a dotted line. And then I would do a test point. And I like to choose the test point 0, 0. If 0, 0 is true, then this whole side of the equation would be true. If 0, 0 is false, then this whole, side of the line would be true. And if 0, 0 is false, then that whole side of the line would be false, so I shade on the other side. So if I put 0, 0 into my equation, I get 0 is less than 1/2 times 0 minus 4. So I get 0 is less than -4, and that is false. So that means I am not going to shade on the side with 0, 0. I would shade on the other side of the line. So that's how inequalities work. A system of inequalities, the shaded region is just what's true for both. And so you would have your two lines would cross, and you would shade just the part that's true for both inequalities. You have 4 possibilities of regions that you would shade often, and so you have to decide